Next, we have something called as angle of repose. So let me put it this way. Say you have two surfaces, or say you have a way wherein you have a plank kind of thing, which you are able to change the angle, something like this. And you keep an object and you want to understand what is the frictional relationship between these two surfaces. Right? This is something that you are able to vary. So this you can change. You can vary this. So you're trying to figure out what is the funda over here, what is the relationship between the two surfaces. So what you can do is you can keep changing the angle to a point wherein it will start sliding. Okay, you keep changing the angle. So let me write this. So you have placed all of this. That's the initial setup. Post that, change the angle, right? Let me write, change the angle. So basically you're increasing it to a point wherein to a point when the to a point that the object starts. Okay, I'm not able to get the language. That the object starts sliding, actually starts to slide. And that particular angle is your angle of repose. Okay, so we are looking at angle of repose. That's it, as simple as that. So let me see the write up. So the basic idea is that angle of repose is the steepest angle you can tilt a slope without stuff sliding down. It's that just right angle, not the word right as in right angle, just right angle where the gravity tries to pull things down, but the friction holds them in place barely. So let me go back to the diagram. Say, if we consider just the object, right, it's in this manner, and what happens? The gravity is pulling it down. That's one thing that we are very clear. Horizontally it is pulling, vertically it's pulling it down, mg. And of course you have a component vertical along the slope. Okay, for that let me draw this. Say this is along the slope and this is perpendicular to the slope. So what you will have is you will have components which will map to that. So somewhere over here. So this is your component along the along a line perpendicular to the slope, and this would be somewhere over here. So that point will be your pulling force, so sliding force. So this is the component which will make the object, I think it's sine theta. So this is theta and this will be sine theta. This is mg cos theta. And of course you have your normal force which counters the mg cos theta. Okay, so this is n basically. It has to be equal to this. So this is your free body diagram. There's one thing missing, of course, friction. That's the whole idea. Friction. We are looking at a static friction which has a maximum possible value. And this theta, when this is maximum, right? Let me go this way. Case of this being maximum, this value this angle value, that is angle of repose. That's all. Repose actually. Repose. Okay, so that's that. Now we have to do the math though. Actually, we just need this diagram itself. I'll just talk about the theta value, guys, because I've seen some of you will get confused. So now we're talking about the angles over here. See, this is the tilt, right? This is your angle theta. Somewhere over here is your perpendicular line. Almost, yeah, that's perpendicular. So this is theta. And this is gravity. And this is also 90 degree. This will be 90 minus theta. So if I just zoom into this part, if we just zoom into that part, what we have here is a line, a perpendicular line, and here too there is a perpendicular line. This is 90 minus theta. This entire thing is right 90, so this has to be theta, because 90 minus theta plus theta is 90. Okay, so this is after zooming into this space. So always remember, this is 90. It's important. You can't just blindly agree that this is theta. Okay, so this is needed. Then we can do the math now. We have to figure out the value of theta. So as per Newton's second law, we have all the forces put together should be equal to m into a. Now, along the slope, what are the forces along the slope? We have mg sine theta and you have fs, and along the perpendicular to the slope, you have the normal force, the reaction force, and mg cos theta. So let us take case by case. Case vertical. So we have r minus mg cos theta is equal to 0, because it's not accelerating. The object is not accelerating along the vertical direction. It's not technically vertical, but vertical along the vertical. And so this is 0. Therefore, r is equal to mg cos theta. We'll need this. This was a simple relation. That's why I started with that. Next, let's move on to along the horizontal. Actually, it's along the slope. And this is along perpendicular to the slope actually. Technically, it's that. K is perpendicular to the slope. As the object is not accelerating perpendicular to the slope. It's technically, actually now we are right, perpendicular to slope. So let me not be lazy about this. Okay, so if I slope down, if I take it as positive, then we have fs max, a negative value, plus mg sine theta should be equal to 0. Again, why? Because object is at rest, right? Object is at rest. So this has to be 0. This is again with Newton's second law. So on rearranging, what do we end up with? Fx max is equal to mg sine theta. Let's call this as 2. So what we have here is 2 divided by 1. So 2, what we have is mx max by your reactional force or normal force, which is equal to mg, this is sine theta and that is cos theta. It's a simple derivation, so I remember, I'm able to picture in my head. If you guys are not able to picture this, please draw, go back, draw and come back to this point. mg, this and this will cancel and we have tan theta is equal to this particular ratio, and this particular ratio is nothing but mu x. So basically angle of repose is same as angle of friction. Okay, that should make sense to you guys. So all the three are one and the same, right? So this is your angle of friction. I hope you guys remember this. And now we are in angle of repose. This has to do with, lifting the surface itself, lifting the surface. But if you look at all of them, the relationship is the same. This is a more practical proof of that particular angle, basically. This is more realistic, doable, right? We are able to do this physically or practically with simple set of materials, and we are able to conclude things. So this is much more handleable, measurable. Yeah, that's a better word. That's what I was looking at. Measurable experiment, which can be easily done, and you guys do it, supposed to do it. Few of the syllabus, they have it. So if you have it, you do it in the class. Okay, so what we looked at is something called as angle of repose. So it's that minimum angle that the inclined plane makes with the horizontal when the object placed on its surface just begins to slide down. That's one of the way of defining it. I keep talking about maximum angle to which the surface will not move. Post that, it will start moving. That's another way to approach it. But yeah, this is what the official definition that I've seen in few books. So I just kept to that. If you get a different definition, write that. And all I did was resolve the vectors along the slope and perpendicular to the slope. And this has to be theta for this reason. And then we have to apply Newton's second law to your, not vertical, but perpendicular to the slope and along the slope. So when you do that, since it's at rest, so they'll be equal to 0, a bit of rearrangement. And you have two equations. If I divide them, we get mu s. And that's that. So end of it, we come back to coefficient of static friction itself. Okay, so I hope you are able to combine all these concepts and able to visualize it, interlink it.